Welcome to this explainer. You know, every successful application starts out wonderfully simple. Literally just one server, one database, and a super straightforward deployment. It's clean, it's elegant, and honestly, it handles your first handful of users perfectly. But what we're diving into today is that wild, crazy journey right after that simple beginning.
Because let's think about it. What actually happens when your app suddenly goes viral? When thousands, or hey, even millions of users just show up at your digital doorstep overnight? How do tech giants like Netflix, Uber, or Amazon scale up to handle massive traffic spikes without just immediately crashing? Well, that's exactly what we're looking at. We're going to walk through the complete journey of scaling a system from literally zero to millions of users, step by step, bottleneck by bottleneck.
So, every massive system, and I mean every single one, begins with a monolith. Picture a single machine doing absolutely everything. Your web server processing the incoming requests, your core application logic running right alongside it, and your database, living on that exact same server. And hey, this works perfectly for small apps. It's cheap, it's super easy to deploy, but as your user base starts to grow, well, the cracks definitely start to show. Which brings us to our very first bottleneck, resource exhaustion. Eventually, traffic spikes. Thousands of users are hitting your site all at once. Your CPU usage absolutely skyrockets. Your memory gets completely maxed out. And suddenly, those lightning-fast database queries are crawling. Just like that, this single server becomes our first major scaling hurdle. Overcoming this resource exhaustion is step one in surviving hypergrowth. The next logical step to fix this is what we call separation of concerns. Instead of cramming everything into one legacy monolith, we split the web tier from the data tier. By decoupling these two, we can now throw more resources at the web servers without even touching the database, and vice versa. Your web servers scale based purely on traffic volume, while the database scales based on storage needs. It's a massive upgrade for both flexibility and overall reliability. Now, with that data tier separated out, choosing the right type of database becomes absolutely critical. You're generally looking at a showdown between SQL and NoSQL. SQL, or relational databases, give you strong consistency and really structured schemas. They're perfect for stuff like financial systems, where accuracy is just non-negotiable. On the flip side, NoSQL databases are all about huge scalability and flexible schemas. They're your go-to for massive distributed systems. So really, the choice just depends entirely on what kind of workload you're dealing with. Okay, so we've optimized the database, but of course, another problem pops up. Because as more and more users arrive, a single web server, even one dedicated entirely to web traffic without a database dragging it down, still has hard physical limits. It simply cannot handle all those incoming requests forever. So what do we do when that single server finally taps out? Well, this brings us to the two fundamental ways to scale your infrastructure. Option one is vertical scaling, basically scaling up. You just upgrade that one web server with a beefier CPU, way more RAM, and a bigger hard drive. It's simple, sure, but there's a hard ceiling. You can't just infinitely add RAM to a single machine. Plus, it gets crazy expensive. And if that one super server goes down, the whole application goes down with it. That's why we have option two, horizontal scaling. Instead of building one giant machine, we just distribute the workload across multiple regular commodity servers. And horizontal scaling really is the absolute foundation of modern distributed systems. By scaling out instead of up, your system becomes naturally distributed and fault-tolerant. You totally bypass those hardware ceilings. Plus, it's elastic. You can just spin up a bunch of new servers during a massive traffic spike and then quietly spin them back down when things cool off. It saves you money while keeping everything online. But as you might guess, horizontal scaling introduces a brand new engineering headache. Now that we have dozens or maybe hundreds of web servers running, we desperately need a traffic controller. When a user tries to access the app, how do they actually know which specific server out of that massive pool they should be talking to? Enter the load balancer. These are absolutely essential. When a user connects, they hit the load balancer first. It acts as this super intelligent middleman, just evenly distributing all that incoming traffic across your entire pool of web servers. And the best part? It gives you instant failover protection. If one web server randomly goes offline, the load balancer instantly detects it and automatically reroutes all traffic to the healthy servers. The end user literally never notices a thing. Just to give you an idea of how this actually looks in the industry, modern systems rely on some incredibly robust tools to do this routing. We're talking about software like Nginx and HAProxy, or cloud-native heavyweights like the AWS Application Load Balancer and Google Cloud Load Balancer.
These are the unsung heroes working behind the scenes, keeping the internet from completely falling apart during massive traffic surges.
So awesome. Our web tier is horizontally scaled, it's load balanced, and it's highly available. Fantastic. But as our application keeps growing, that separated database we talked about earlier, it eventually gets overloaded again. In most modern apps, read-heavy operations are the main culprit. Think about it. Users are constantly refreshing their feeds, scrolling profiles, and reading data way, way more often than they're actually creating new data.
So the fix here is a really brilliant architectural move: database replication. What we do is take our data tier and actually split the read operations away from the write operations. We keep one primary database, the master, and that handles absolutely all the data changes, like inserts, deletes, and updates. But it continuously copies that data over to multiple read replicas. Now, all those incoming read requests get routed to the replicas, letting us process way more queries in parallel and massively speeding up performance.
But as we're learning, every new architectural solution brings its own set of complexities. Because data actually takes time to travel from that primary database over to the replicas, we get something called replication lag. It's basically a tiny delay in data synchronization. So for a split second, a user might publish a new post, hit refresh right away, and not actually see it yet because the replica they're reading from hasn't gotten the update. Managing that little inconsistency is a huge part of scaling at this level.
Now, to take even more pressure off that database and practically eliminate latency entirely, we have to push data all the way out to the edges. We do this in two ways. First, we set up an in-memory cache using something like Redis. This stores super popular, frequently requested dynamic data right in RAM, so we can serve it up lightning fast without ever bugging the database. Second, we use a content delivery network, or CDN, for static assets. Instead of a user in Tokyo waiting for an image to travel all the way from a server in New York, the CDN just keeps a copy of that image geographically close to the user at an edge node, serving it instantly.
So by stacking together load balancers, database replication, caching, and CDNs, your architecture is officially robust enough to handle millions of concurrent users. It's a beautiful thing. But I'll leave you with one final thought to chew on. You've built this incredibly elastic, fault-tolerant system in one physical location. But what happens to those millions of users if that entire data center goes down, or a massive natural disaster takes out power to the region? Well, that is the ultimate test of scale, bringing us into the wild world of multi-data center redundancy. But hey, that is a deep dive for another time. Thanks for joining me for this explainer.